So let us finally do another very cool application of WordNet. So in this application, we consider the task of semantic relatedness and or equivalently, as we will treat equivalently, the task of semantic similarity. So there are some authors and people and researchers that make a distinction between semantic relatedness and semantic similarity, but we will use those two concepts equivalently in our brief exposition now. Now, semantic similarity is a very important concept in natural language processing, because if we have a good understanding of what is semantically similar, either on the level of individual words or on the level of whole sentences, then we have a really powerful tool. Imagine what we can do with it. On the one hand, for example, we could build an evaluation system that allows us to evaluate how good we could build an evaluation metric that allows us to evaluate how good any machine translation system is, for example. Let's say you have a machine translation system translating from French into English. And now let's further assume for any given French input set, you also have a human reference translation produced by some human expert. Now, what you can do is if you want to evaluate the quality of your machine translation system, you should evaluate the semantic similarity between the human expert translation and what your machine translation system is producing. So you compare two English strings in this case, and you want to compare them whether they are semantically equivalent, because this is all what is machine translation about, to make a semantic equivalent translation in another language. So if we have a system that can judge semantic similarity, it would be very well suited for being a candidate for such an evaluation metric. Or similarly, imagine a web search in your favorite web search engine. If you type in a word such as cab or maybe a whole string, where is the next cab, you'll hope that the search engine is clever enough to understand that cab and taxi are similar, because maybe there are many more relevant web pages with the words taxi. So you do not want to lose those web pages when you type in cab. So now let's imagine an approach to use WordNet to capture the concept of semantic similarity. And for this, let us have in our minds one WordNet hierarchy, and recall that these WordNet hierarchies, so now it looks like these are words, but in reality you know that those hierarchical relationships, or those relationships, are really between synsets. Now we have those synsets here organized in a hierarchy such that we can say a baleen whale is a whale, and a whale is a cetacean, and a cetacean is an aquatic mammal. Okay, so we have these hierarchical relationships, and now let us figure out whether let's look at the word right whale and check its intuitive semantic similarity to gray whale. So we would say here, because right whale and gray whale, they have a direct common ancestor, a common hypernym, probably they are very closely related because they are both baleen whales, right? So their earliest common ancestor there is a direct parent. Now if we check a right whale with a killer whale, then we would say, well, a killer whale first of all is a dolphin, and a dolphin is a toothed whale, and a toothed whale is a whale. So a killer whale is a whale, and a right whale is also a whale. But here you see that their common ancestor is much further distant from those two, and it's much further up the ladder. So we would argue that those two are less semantically similar. And this is now what we want to exploit in one algorithmic idea to compute semantic similarity using WordNet. So let's say we get the synset for right whale, as we've just seen. We get the synset for orca, for minke whale, for tortoise, and for novel. So right, so this is a very different word. Then we check what is the lowest common hypernym of when we have right whale versus minke, we see it's baleen whale. It's this one here, right? Even though this is now not in our graphic. When we check what is the lowest common ancestor between the right whale and the orca, then again orca is not here, but it's also again the whale. And if we check what is the lowest common ancestor, the lowest common hypernym between the right whale and the tortoise, now also tortoise is not here, but it will be further up. It will be further up the ladder, so it even goes up here to vertebrate. And if we go for novel, we even have to go to the very top of the WordNet hierarchy, to the entity. So intuitively, if we have to go up so far, then those two words are probably not very semantically similar. And we can actually, like for each of those common ancestors, we can quantify how deep down in the WordNet hierarchy they are by checking the minimum depth. So we start from the top and look at the shortest path to reach. So there may be multiple paths to reach a synset, and we look for the shortest such paths. And we see that baleen whale is well, entity is at the very top, and vertebrate is also very much on the top, and baleen whale and whale are more further down the ladder. So from these, this quantification, we would say that synsets that share whale as a common hypernym, that they should be more closely related than synsets that share entity as the lowest common ancestor. Okay, and then you can indeed compute semantic similarity or semantic relatedness using such ideas, and it's already implemented in NLTK, so that you can indeed, if you type in right whale and you type in path similarity to minke, it gives you a number, and you see those numbers are intuitively those numbers that we would expect. The lower, the less semantically similar. Now, as one remark here, the numbers themselves apparently do not have so much meaning for you, so this is not so much important, but the relation between the number is important. So if you have two numbers, the one which is bigger indicates higher semantic similarity. So that is how you can use WordNet to get the semantic similarity of two objects, even if they are not in the same synset, let's say. Okay, now let me give a brief excursion, because I have indicated this earlier, that in the lecture what we are doing is quite elementary, and there are other approaches nowadays to many aspects that we are computing, and there are more novel and better approaches to those aspects. So I would say that nowadays very few people still use WordNet for semantic relatedness or semantic similarity, or to be more precise, I actually know nobody who is doing this. So I'm a natural language processing person. Maybe there are some linguistic folks who are still doing this, but in the natural language community, natural language processing community, there are very few people who do that. Instead, what people do is they use word vectors, also known as word embeddings, to compare two words. So what happens here is that each word gets assigned a vector, and this vector represents its meaning. The word vectors are derived from neural networks, as we have briefly discussed in a previous lecture. The network is trained, so you optimize somehow your network to solve a semantic task. And this semantic task is predicting context word. So for each word, we would predict the words that are in the neighborhood of this word. So for example, for the word man, you would predict that one neighbor could be an article such as the or a. It could also be a word like tall or small, and you would predict such neighborhoods for every word. And I've already indicated earlier that synonymy, so meaning equivalence, could be defined versus context. So if you can exchange two words in all contexts, that is, if they have the same context every time, then those two words are semantically equivalent, or at least very, very similar. So semantic similarity can be predicted versus such a contextual definition, right? And this is what those networks are learning, and then they learn to get a numeric representation, like a vector representation for each word, such that the context can easily be predicted from that numeric representation. And then if two words are very similar, that is, they have the same context, then they should also get very similar vector representations. And this is, in a nutshell, in a very brief and simplified nutshell, what like models like word2vec, if you have heard about them, are doing, or even more modern, popular, more recent approaches such as Elmo or BERT. So once we have such vectors, we can just compare the vectors. So we're in a math world. We don't need to traverse graphs or something. We can just compute a similarity between vectors. And there are many measures for computing similarity of vectors. One of the most popular measures is the cosine similarity. And the advantages, if we have such an approach, is there are multiple advantages over using WordNet. And those advantages, I will briefly list them here. First of all, it's more powerful. So if we go to real data and compare the semantic similarity measurements from WordNet to those with like those word vectors, we see that the word vectors perform better. So they are the similarity that those word vectors give are more like those similarity values that humans would also give. So if you have two sentences or two words, such as whale and orca, the similarity that WordNet gives is not as good as the similarity that word2vec gives. So this is the first thing. The second thing is using those approaches like word2vec and inducing those vectors are much less costly. Why are they much less costly? Because they don't need any knowledge resources. So for WordNet, we need to create a whole hierarchy of words in a language, right? Like English. So we need to compute synsets, we need to derive those hierarchical relationships, and all of this has to be encoded by a human being, right? And then we would have to repeat this not only for English, but also for French, German, etc., etc. So it becomes more and more costly. And also keep in mind those languages are all changing over time. So the WordNet for the 1900 English does not look like, or would not look like, the WordNet for the 20th century English. So this is really a high cost, because in all those cases we need to involve many humans and we have to pay them. Whereas if we use word2vec, we have to include no humans at all. We have to do nothing, just get arbitrary, let's say Wikipedia text in large quantities. And yeah, and the third thing, that's already what I indicated. It generalizes to arbitrary languages. So really we can do this for German, we can do this for English, for German, for Turkish, for Chinese, for any languages. We just need a big corpus of Wikipedia data to compute our word vectors. But if we want to do the same, with WordNet, in each case we have to hire a lot of humans. And to just give you a small visualization of how those word vectors look like. So those word vectors look like, first we have our words, then to each word assigned is a vector. So this is just an array of numbers, and in this case it's 1, 2, 3, 4, 5, 6, 7 numbers. So each word has associated 7 numbers. Maybe we can interpret those dimensions, but in most cases we cannot really interpret those dimensions. And now we can, of course, we could plot those vectors in a vector space and in a visual representation for humans, but humans cannot see in 7 dimensions, so we first have to reduce it down to 2 dimensions. And then in 2 dimensions it would look like this, that like Here we have dog, here we have houses, so they are far apart. And cat and kitten are very close by because they are intuitively very similar, right? And if in such a space, we can immediately just give the similarity between words by calculating their distance, right? So here these two are close by, these two are further apart. Okay, so this concludes lecture number 5. We talked about WordNet, and we talked about synsets, lexical relations, and semantic relationships in this last part. If you want to keep a picture about WordNet, keep it as a graph, so there are words in there, or more appropriately synsets, and those synsets are related by hierarchical semantic relationships. Why is it useful? Because we can compute text similarity, we can use it for information retrieval, to build better web search engine, as I have shown you, or as I have outlined to you. We can also, if we would have something like this and we have a library catalog, we could, via semantic similarity, we could better find the things that we are looking for. And we can use this for other applications. So semantic similarity is a very high-level concept in natural language processing. So you can also do this maybe for doing inference, right? So let's say we have the example: after his visit to Berlin, the president flew to Paris, and then we would want to find out whether the president is in Berlin. And we as humans, we know, okay, from these two statements, no, this is actually not the case because the president is now in Paris. But by, let's say, computing the similarity between those two statements, like the statement and the question, or the first statement and the second statement, we would maybe find out that the president is not in Berlin, because if we had another statement like the president is in Paris, then maybe the semantic similarity measurement would give us, would indicate to us that this sentence is more similar to the sentence the president is in Paris than it is to the sentence the president is in Berlin. So we can use semantic similarity for many other natural language processing downstream tasks. And with this we conclude the 5th lecture. And if you want to prepare for next week, you recapitulate all the basic concepts that we have done in this lecture. This is not only WordNet but also word lists, and more generally lexical resources. Check the practice class and go on, read chapter 3 in the NLTK book.